Good morning. We are going to start on isolated DC-DC converters in today's class. We had looked at non-isolated converters where the input and output side are sharing the same ground. So, in those cases, if there is a disturbance on the supply side, it will affect the load side. And similarly, if there is some kind of disturbance on the load side, it can affect the supply side. So, both can kind of interfere with each other because of circulating currents that can flow between the input and output side. So in that sense, it is not a very safe arrangement when we have the load to be probably working at, let's say, a few watts level, whereas the source to be working at kilowatt level. So it's not a good situation at all. And one more disadvantage of non-isolated DC-DC converter is that the gain will be pretty much limited. What I mean is, if I am having a 24-volt source and I want to get only 2 volts out of it using a buck converter, what you need as the gain is 1 by 12, 1 divided by 12. Such small gain, it is very difficult to obtain from non-isolated converter. Similarly, let us say I have a 5-volt source and I want to get 100 volts. So it is essentially 1:20, which is using a boost converter we need to obtain. And such gains become extremely difficult to achieve. The best gain you may obtain from a buck converter may be 1 by 2, that is 0.5. Similarly, from the boost converter, you may be able to obtain a gain of about 2. So from 5 volts, you may be able to obtain 10 volts. Similarly, from 24 volts, you may be able to obtain 12 volts. But if I want to have the bucking or boosting much more than this, it's going to be really difficult. So in those cases, if we have an intervening transformer, then with the help of the turns ratio, we will be able to obtain a good amount of or a large gain. Large gain will be obtainable in those cases. So once you have an intervening transformer, we call that as an isolated DC-DC converter topology. So isolated DC-DC converters invariably will have a high frequency transformer. The transformer that are used are generally high frequency transformer. So you would be able to miniaturize those transformer as well as the converter. So if you are looking at, for example, the normal regulated power supply we use in our laboratories, they are all very big because of one reason. So let us say we want a 15 volts power supply. Then normally what we try to do there is, first of all, we will have a 230 volts AC, which is coming from our power grid. And that is going to be, first of all, stepped down using a 50 hertz transformer. So we are going to have, let us say, from 230 volts, maybe we would like to get 15 volts or 20 volts. So this is a 50 hertz transformer. And as we mentioned earlier in one of the classes, low frequency transformers will always be bulky because E is proportional to frequency and flux. And if I say this is only 50 hertz, the flux is going to be much higher in this particular case. And if the flux is higher, we are going to have the flux density also defined for a particular material already. So we need to have really a larger cross-sectional area in those transformer core. And that is one reason why the transformer core itself becomes bigger. So you're going to have the transformer size is going to be much bigger in that case. Whereas in this particular case, because of this transformer, what we are talking about, it will be a very big transformer. Now, this output of 20 volts or whatever will go into a rectifier. So if we have a rectifier, we are going to have generally an oscillatory waveform. What we get out of the rectifier from here will be an oscillatory waveform. And to filter out those oscillations, we will have to reduce the voltage ripple. We will have a bulky capacitor, big capacitor. And it will be an electrolytic capacitor. And electrolytic capacitors generally fail quite easily. They are bulky. So reliability becomes a big issue because of this. And also, the input current, what we get here will be peaky current waveform. It will not be sinusoidal. The current, what we get here, if I may call this as IS will be peaky. So power quality will be affected very adversely. So unless we put something like a power factor correction circuit, PFC, power factor correction circuit, we are not going to be able to get a sinusoidal current. So this is a non-sinusoidal current, and which can be made sinusoidal only with some filter or power factor correction circuit. Now, from this, whatever we have got, this will be a steady voltage, which may be 20 or 25 volts that we get from this. And that has to be taken further to a voltage regulator circuit. So this voltage regulator IC, which is available, for example, 7805 will regulate the input voltage, which is greater than 5 volts to plus 5 volts. It will regulate, basically it has a transistor working in active region. So it is going to drop some portion of the voltage. Let us say I have 20 volts, 15 volts will be dropped in the transistor, only 5 volts will come up at the output. So the transistor working in active region and dropping 15 volts will have a huge power loss. That is the reason why regulator ICs or regulator circuit will be generally getting heated up unduly. So first of all, efficiency will be poor, and also to regulate this voltage, it is dissipating a huge amount of heat. So we need to have big heat sinks to dissipate this power. So that is the reason why the overall voltage regulator, inclusive of the heat sink, will be really, really bulky. So now what comes out of here will be a regulated voltage. So this will be a regulated output, what we get from our normal regulated power supply that we see in the lab. So 7805 is a regulator IC available for plus 5 volts. Similarly, we may have 7905, which will give us minus 5 volts. And similarly, 7815 is available for obtaining plus 15 volts, and 7915 is available for obtaining minus 15 volts. So these are some of the regulator ICs that are available in the market. So that is one reason why regulated power supplies are bulky. The first reason is 50 hertz transformer. The second reason is the voltage regulator and associated heat sink. Rather than this, we have started using switched mode power supply in many of the new appliances, inclusive of TV or laptops or personal computers. So switched mode power supply, which are even of 500 watts or 1000 watts rating, they all become really, really small because of one reason, and we use high frequency transformer. This is one reason why they have become much smaller. So what happens in a switched mode power supply is, again, we have a 230 volts single phase 50 hertz being fed to these power supplies. And after that, we directly have a rectifier. And rectifier's output normally will not be connected directly to the capacitor. Rather than that, we will have a DC to DC converter. And this DC to DC converter, in fact, in most of the cases, will be an isolated DC to DC converter. So what we are actually getting here at this point, here it is sinusoidal voltage, what we are feeding. And what we are getting here is a rectified voltage with a lot of ripple. Whereas what we are getting here will be actually completely regulated steady DC voltage, which will be of very low magnitude, maybe 5 volts or 10 volts or 15 volts. So inside an isolated DC-DC converter, actually there will be, first of all, an DC to AC converter. What you get from here as the oscillating voltage, that will be first of all converted into AC with high frequency. So there will be a DC to AC converter at high frequency conversion, and you will have a transformer, high frequency transformer, which will be converting from high voltage, because what you obtain here will be of the order of, again, 230 volts RMS or 230 times root 2 volts peak. So about 325 volts peak you are going to get here, which has to be converted into maybe close to 5 volts, maybe close to 10 volts. So you may have multiple secondaries sitting here. So this may be 5 volts, this may be 15 volts, and this output, what you get, will be fed to a rectifier. So you are going to have a rectifier at this point. So this may be rectifier 1, this may be rectifier 2, and so on. So this is the kind of rectifier that you are going to see. So multiple secondary windings may be there, but only one primary winding may be there. And this output will be, for example, a 5 volts DC output. And this may be a 15 volts, and you can have even reverse output. That's not a problem, because they are all individually having their own ground and they are all isolated from each other. So this DC to DC converter, what you see here, consists of a DC to AC high frequency conversion and then a transformer. So this will be a high frequency transformer, and at the output stage there will be a rectifier. So there are multiple stages of conversion within the switch mode power supply, and still the size will be limited because we are really not having 50 hertz transformer, and we are only having no regulated IC. So no 50 hertz transformer and no regulator IC. So this makes essentially the entire SMPS somewhat miniaturized. And when space is very limited, we really want to have this kind of a circuit in place. So the isolated DC-DC converters have become extremely popular because of many power supply demand from the consumer side. Consumer electronics, all of them use SMPS. And second thing is, in electric vehicles, if we look at isolated DC-DC converters, We use them for all the auxiliaries like lighting, infotainment, information processing, and also uh, entertainment. Like if we want to play some video, we want to play some music, all of them will require these kinds of power supplies. Even for heating, ventilating, and air conditioning system, these can be used. And for electronic control units, all of them use the isolated DC-DC converter in electric vehicle. One more thing where it is extensively used is in battery charging. Whether it is onboard charger or off-board charger or wireless charger. All of them use isolated DC-DC converter, and particularly one converter called dual active bridge, which we will be discussing finally in the isolated DC-DC converter topologies. So, I am going to discuss primarily in isolated DC-DC converter. I am going to mainly discuss 4 topologies in this particular course. One is going to be flyback, which is the simplest of all the isolated DC-DC converters, which is generally used for less than 100 watts rating. The second one, which we are going to discuss, is half bridge, which is generally used for anything less than 500 watts, not above that, preferably. So this generally is used in most of the SMPS for PCs. And the third one we are going to discuss is full bridge, which is used along with solar PV and large power supplies that are used probably for welding or telecom tower. All those things generally use full bridge power converter. So this can be used anywhere between 100 watts to few tens of kilowatt. So the fourth one which we will be talking about is dual active bridge. Dual active bridge is again used for very high power rating. If we are talking about onboard or offboard chargers, and for wireless power transfer, it may be for lower ratings. So we will be looking at all these different types of isolated DC-DC converters. DAB, I will be probably taking up in the next class. Rest of the isolated DC-DC converters, I'll be taking up in today's class. Apart from this, there are also other kinds of isolated DC-DC converter, forward converter, push-pull converter. All these things are also very popular isolated DC-DC converters. If you want to study about them, you might like to refer to any of the power electronic books. Because we have limited time, I'm not really planning to go into those converters as well. So let's first of all start with flyback converter. So flyback converter has a topology somewhat like this. We are going to have an input, which is say V source. Rather than that, let me write this as V in, input voltage. And I'm going to have a transformer primary connected here. And I'm going to have a switch which is connected here, which is going to switch in and switch out V in across this transformer's primary winding. But this is going to do it at a very high frequency, because of which otherwise generally DC you cannot apply to a transformer. But the transformer here is being switched at high frequency, so it will not enter into saturation. Otherwise, transformer will behave like a short circuit for any DC, because you are going to say L di by dt is equal to V, voltage across transformer. And if we are going to have it reaching steady state, di by dt will be 0, because of which voltage across the inductance will be literally 0, which will be like a short circuit, which is deadly for applying DC to a transformer. That's why it could be really deadly. But here we are doing it at high frequencies, so it's not a problem. Now here is the core across the transformer, and this is the secondary side. Now, if I'm going to talk about this as dot, where the current is entering, so the current enters here, so we call it as a dot. We are going to have the dot for the other one on this side. So if I say this is positive at this point, this is going to be positive at the same point, at the same instant of time. And we will have a diode connected here. Sorry, just a second. We'll have a diode connected here, and we will have a capacitance as acting as a filter, and here is the load. So this is the way it is going to be connected. So this dot notation, just to give a little bit of explanation, if I'm going to have a transformer which is having a core somewhat like this, and let us say I am having a winding which is coming out like this. I hope you can visualize. So this is the front side of the coil, back side is hidden. And again, I'm going to have somewhat like this. So this is going to come out like this. So if I am connecting, let us say, a voltage source like this, the current is entering like this and it is coming out here. So whenever a current is coming out, it is as though you are seeing the front side of the arrow. So I am showing this as a dot. Whereas when the current is going in here, I am showing that as a cross, which is the back side of the arrow. So I'm going to have dot here and cross here. So as per the right hand rule, we are going to have a flux which is actually in downward direction. We are going to have a flux which is going to be in downward direction, and it is going to go like this and complete the path like this. This is how the flux path will be. Now on the other side, I am again having a coil which is wound. So let us say my coil is wound in this way. So this is going like this, and this is going to go around, and it is going to go like this. So this is how the coil is wound. Now this is coming out like this. This is the coil, how it is wound. So if I look at it this way, this flux, what is actually produced by the primary, and the flux which is produced by the secondary, they have to cancel out with each other. Otherwise, the flux will go to literally infinity. So even this flux has to be exactly in this direction, so that it opposes what is coming out of the primary, or what is created by the primary. So if the flux has to come this way, then I should have dot here, and I should have cross here. So which means I should have the current basically flowing out like this, and the current should be flowing in like this. So if I am connecting a load here on the secondary side, because in the primary side I have connected a source, I should have the current flowing out in the load like this. So this should be plus and this should be minus. So that's what we mean by saying if I am having plus here and minus here, so I would call this as dot. And similarly, if I'm having plus here, this should be my dot. That's what I mean by saying dot is at the bottom and dot is at the top here. So I just wanted to give you a little bit of how the coils are wound and how the entire thing looks like. So now this is the switch here and this is the diode here and this is the capacitance and this is the resistance. Okay. Now when I am actually having S on, I am going to have the primary essentially being short circuited along with the switch. So we will have current building up across this transformer, which is consisting of a magnetizing inductance between these two. So I have to write Lm delta ILM, which is building up right now, the current, equal to V in times dt. Okay. And when we are having plus here, the plus is at the bottom as far as the transformer is concerned. So diode is reverse biased on the secondary side. So it is not going to conduct. So what we have is if we are having some stored energy in the capacitance, we are going to have a current flow like this. This is how the current flow is going to be during this particular situation. So the capacitance is discharging into the resistance. So if I try to draw how the waveform is, I'm going to have essentially Lm times delta ILM, or this is ILM, which is actually building up the current during d times t. And when I am going to have this switch completely turned off, the inductance current abruptly cannot go to zero. So it will try to release its energy. When it is trying to release its energy, this will become plus and this will become minus. And because this becomes plus, the diode will be forward biased. So when S is off, we have reversal of polarity across Lm, because of which diode on the secondary side is forward biased. Because it is forward biased, it is going to start conducting. So we will have a current that is flowing from the secondary side of Lm, and it is going to flow into the capacitor as well as to the resistance. So we will have basically the current coming down like this, which is not visualized from the primary side, but only in the secondary side. Now this will repeat itself like this. So this is going to be T off, and again this is going to be T on, and this is going to be T off. So this repeats itself. Now, when S is off, I should be able to write the equation. If I visualize it from the primary side, it is going to be the output voltage, what is available, if I may call that as V naught. So V naught multiplied by, if I may call this as NP number of turns on the primary side and NS number of turns on the secondary side, V naught times NP divided by NS. That is going to be the voltage visualized from the primary side. That multiplied by 1 minus d times t, that is going to be equal to Lm times delta ILM, where ILM is coming down. So equating these two, I should be able to write V in D equal to V naught NP divided by NS multiplied by 1 minus D. So from this, I can write V naught divided by V in equal to D divided by 1 minus D multiplied by NS divided by NP. Because of this NS and NP also coming into picture, we will be able to get a huge or large gain depending upon what are the values of NS and NP. Not only duty ratio matters, the NS and NP value also matter. So if you look at the primary side current, that is only until dt. And if you look at the secondary side current, it is available only during the off interval. So you are going to have the current somewhat like this on the primary side. And if I look at the secondary side current, I'm going to have the current somewhat like this during the secondary side. This is how it will be. So this is the primary side current, and this is going to be the secondary side current if I'm looking at 1:1 as the turns ratio of the transformer. So these are all plotted with respect to time. And if I try to look at what is the average current across the load, the average current will be somewhere here, because this is only averaged over the complete complete period. We are looking at the entire time period T. So it is going to be averaged over the entire time period T. So I should be able to write the I naught is whatever is IL max and IL minimum, whatever is the current through the magnetizing path, and that has to be divided by 2 because area across the trapezium, and that has to be multiplied by 1 minus d times t, and it should be averaged over t. This is what is going to be the I naught value that I get. Okay. One thing you have to remember is if I am talking about I naught on the secondary side, this is also, these values also should be taken on the secondary side. So the turns ratio will always come into picture when I turn the current from the primary side to secondary side or secondary side to primary side. I have to use the turns ratio accordingly. Let me try to work out one problem on or numerical example on flyback. So let's try to look at one numerical example on the flyback converter. The problem statement goes somewhat as follows. A flyback converter has the following specifications. V in is 24 volts. V out is 5 volts. Resistance on the output side, the load resistance is 5 ohm. Switching frequency is 40 kilohertz. LM value of the transformer, the magnetizing inductance value is 550 microfarad. And primary to secondary turns ratio is 2.5. Now, what will be delta ILM? So that is what is the ripple in the inductance current. And what is average value of ILM? That is the current through magnetizing inductance. And if delta VC naught divided by VC naught should be less than 1%, what will be C value? That is capacitance value. This is what is being asked. So let's try to work out the solution for this. First of all, we derived the V naught by V in D divided by 1 minus D multiplied by NS by NP. So we say V naught divided by V in is equal to D divided by 1 minus T multiplied by NS divided by NP. So this is actually 5 divided by 24 multiplied by D divided by 1 minus T, 1 divided by 2.5. This is what is the value that is being given as the turns ratio, from which you can calculate what is D. So this is 6.25 divided by 24 equal to D divided by 1 minus T. So from which D can be calculated as 0.2063. Please verify the calculation. I have just done the calculation corresponding to this. So this is the duty ratio that we are getting for this converter. Okay. Now we drew the waveform here. We said that this is I naught, and we also derived the expression corresponding to I naught. And we said that the capacitance is giving the current during the on interval of S. So we are actually having the capacitance current. If we draw, we should draw the capacitance current as though it is equal to I naught minus I naught, because it is supplying the current to the load. So it is minus I naught during dt, and it is going to be whatever is it will go up till IL max, and then it will come down to IL minimum, and this is during 1 minus d times t. This is going to be 1 minus d times t. So I can say this is delta Q, which is being absorbed by the capacitor, and this is delta Q, which is being given away by the capacitor. So delta Q, which is equal to C times delta V naught, will be equal to dt times I naught. So this I can write this as d divided by frequency of switching, and I naught is V naught divided by R. So I should be able to write this as delta V naught divided by V naught will be equal to D divided by FRC. This is very similar to what we got in terms of the equation for capacitance or voltage ripple, even in boost converter or buck boost converter. We got this as the same equation. So I'm going to use this here. So I can write D divided by FRC is equal to delta V naught divided by V naught. And that has to be less than 1% according to the specification that is given. So I should be able to write this as D divided by FRC equal to 0.01. So I can say C should be equal to D, which is 0.2063 divided by 40 kilohertz. So which is 40 divided by multiplied by 10 power 3, and resistance is given to be 5 ohms, and 0.01 is the value of the voltage ripple. So this capacitance comes out to be 103.15 microfarad. So this is the capacitance value we have arrived at. Now, what is the value of ILM and what is the average value of ILM? These are the two questions that are being asked. If you may recall, we wrote LM times delta ILM is equal to V in multiplied by dt. This is one thing we wrote when we analyzed the. So we said this is what this is one expression we wrote during on interval. So we can use that. And we can say delta ILM equal to V in, which is 24 volts, D, which is 0.2063. T can be written as 1 by F, so 40 multiplied by 10 power 3. And LM is already given as 550 microfarad, so which is 10 power minus 6. So delta ILM from the primary side. We are writing this from the primary side or source side. So we can write this, we can calculate this, and this comes out to be 0.225 ampere. And again, if we have this delta ILM, we can say IL average plus delta ILM by 2 equal to ILM peak. Similarly, we should be able to write IL average minus delta ILM divided by 2 equal to ILM minimum. This also we know, and we can say ILM peak minus ILM minimum will be delta ILM. So we have an expression for ILM peak and ILM minimum. Similarly, if you look at how we calculated I0 average, it said ILM max plus ILM minimum by 2 multiplied by 1 minus t. That is what was I0. So I should be able to write that also. I0 average, which is actually 1 ampere, should be equal to ILM peak plus ILM minimum divided by 2 multiplied by 1 minus d. But this is essentially on the secondary side. So I can convert that into primary side by using the turns ratio, and turns ratio is 2.5. So I can simply say 1 multiplied by 2.5 ampere, which is from the primary side. Because turns ratio, the voltage will be stepped down on the secondary side, whereas voltage with the voltage ratio, the current will be stepped up on the primary side. So this is 2.5 ampere equal to ILM peak plus ILM minimum multiplied by 1 minus d. 1 minus d is 1 minus 0.225 2063 divided by 2. So I have two equations now. One is IL maximum minus IL minimum equal to delta ILM, which came out to be 0.225 ampere. And IL maximum plus IL minimum equal to 2.5 multiplied by 2, that is 5 divided by 1 minus 0.2063. So this is essentially, these are the two equations that can be calculated from the primary side, from which we can calculate what is IL max and IL minimum. And I can say the average value will be ILM peak minus delta ILM by 2. So IL max minus delta ILM divided by 2 will be IL average. So I'm sure using equation number 1, equation number 2, and equation number 3, you should be able to calculate what is IL average. IL max and IL minimum can be calculated from 1 and 2, and from equation number 3, you can calculate IL average. Okay? So this is one example I wanted to just work out on flyback converter. Now let us just look at half bridge and full bridge converter. So half bridge converter. The half bridge converter circuit is somewhat like this. You have this as the input voltage, which is divided into two halves with the help of two equally charged capacitors. So let me call this a C, this also a C. Maybe this is C1 and C2 so that I'll be able to understand the working clearly. So this is going to have C1 is going to have V in divided by 2. Similarly, C2 will also be charged to V in divided by 2. So we will have plus here and minus here. Similarly, plus here and minus here. Now I'm going to have one device connected here like this with the feedback diode, and one more device connected like this with the feedback diode. I'll explain the importance of feedback diode when we are discussing inverters. Just assume right now that the feedback diode is also there. That's it. So let me call this device as S1 and let me call this device as S2. And I'm going to have from here, this is connected to the transformer's primary on the top side, and this is going to be connected at the bottom side. And I'm going to have here a center tap rectifier like what we discussed earlier, so that it will have only one diode conducting during the positive half cycle, one more diode conducting during the negative half cycle. And I have an inductance filter, a capacitance filter, and the load sitting here. Now this is going to be connected from the center tap. So this is C, this is R. So when I am having S1 on, I am going to have the current flowing from C1, and it is going to flow through S1, and it will go through A and B, and it will return like this to C. So it will be C1, S1, A, B, and then back to C1. So what is coming across AB? So VAB will be equal to V in divided by 2. So under such a condition, we are going to have, if we call this as NP is to 2NS as the turns ratio. So V in by 2 multiplied by NS by NP. So the voltage that is conducted to the output will be on this side. It is going to be, if I may call this portion as P and this point as Q, Vp is going to be V in divided by 2 multiplied by Ns divided by Np. That will be the voltage at P. Whereas voltage at Q, if I may call this as V naught, so voltage at Q will be V naught. So VLX is going to be equal to VPQ, which will be essentially V in divided by 2 multiplied by NS divided by NP minus V naught. This is going to be VLX. And that is going to be equal to LX di by dt. So if I may write this as delta ILX, there is an increase in the current divided by dt by 2, because the same thing will repeat itself for S2 as well. So S1 is on for dt by 2 duration. And S1 and S2 both are off for 1 minus d multiplied by t by 2 duration, during which the inductance is going to supply the resistive load now. So it is going to be exactly like a buck converter. So I should say V naught multiplied by 1 minus d t by 2, that will be Lx times delta ILX, and current in ILX is decreasing during this trend, whereas here ILX is increasing, okay, during this particular portion. So I should write Lx times delta ILX, which is equal to V in divided by 2 Ns divided by Np minus V naught. That is going to be multiplied by dt by 2. This is during S1 on. Whereas the same thing I can write Lx times delta ILX equal to V naught multiplied by 1 minus d times t by 2. This is during S1 and S2 both are off. So this makes up for t by 2 duration. The same thing will be repeated with S2 on and S1, S2 off. That will be for the next t by 2 duration. So this will be repeated again and again for every cycle. So I should be able to write this as V naught multiplied by 1 minus d times t by 2 equal to V in divided by 2 Ns by Np minus V naught multiplied by dt divided by 2. So this t by 2 and this t by 2 I can cancel. So I should be able to write this as V in divide, let me write this clearly. So this V naught times d, I can bring it to the other side. So I can write V naught equal to V in divided by 2 Ns divided by Np multiplied by D. So I can write V naught divided by V in equal to Ns divided by 2Np multiplied by D. So this is the conversion ratio as far as half bridge is concerned. This 1 by 2 is coming because we have divided that voltage into V in divided by 2 here and V in divided by 2 here. That is the reason why we are getting 2 factor in half bridge. So the output depends upon what is the turns ratio and what is D. So the turns ratio can actually make a big difference in terms of the bucking factor or step down factor in the case of a half bridge converter. So this is going to be V naught divided by V in the case of a half bridge. Now let me explain full bridge converter also. Only difference is going to be I am going to have no capacitors that are actually looking at, halving the voltage on the primary side. So I'm going to have one switch here and one more switch here, which will conduct together. So let me call this as S1 and this as S4. Similarly, I'm going to have S3 here and S2 here. And of course, I will have feedback diode across each of these devices. Now, I am going to connect the transformer from here, which is the primary, and I'm going to have the secondary connected here. So this is going to be again NP is to 2NS. Now again, I will have a center tapped rectifier connected like this. And I'm going to connect from the center tap an inductance, a capacitor filter, and a resistance connected somewhat like this. So I should call this as D1, this as D2, and I'm going to call this as LX, this is C, and this is R load. And what is coming up here is V naught. So when I have S1 and S4 on, I'm going to have, if I call this as V in, voltage across LX will be Ns divided by Np multiplied by V in minus V naught. That is going to be the voltage. So I can write Lx times delta ILX will be this VLX times dt. And when all 4 switches are off, let me write this as dt by 2 because this will repeat itself again for S1, S4 on and S3, S2 on. So when all 4 switches are off, I'm going to have Lx times delta ILX equal to V naught times 1 minus d t by 2. Now, when I'm going to have S2 and S3 on, the same thing repeats itself. I'm going to have Lx delta ILX equal to Ns divided by Np times V in minus V naught multiplied by dt by 2. And again, I'm going to have for the next Lx delta ILX when all 4 switches are off. I'm going to have again that is equal to V naught multiplied by 1 minus d by 2. So these two correspond to first d by 2 and these two correspond to next d by 2, which make up for one full cycle. Okay, so I should be able to write this as VLX dt by 2 for the first dt by 2 period. I can write that is equal to Ns divided by Np V in minus V naught multiplied by dt divided by 2 equal to V naught multiplied by 1 minus d by 2. So I can cancel this t by 2 and this t by 2. And this V naught d, I can take it to the other side. So V naught equal to Ns divided by Np multiplied by V in times d. So I can write directly V naught divided by V in equal to Ns divided by Np times d. Only that half factor is missing as compared to half bridge. In half bridge, we had this Ns divided by Np d by 2 equal to V naught by V in. This is what we got in half bridge. Whereas in full bridge, what we have is that half factor is missing because of the fact that the entire V in comes across the primary winding when S1 and S4 are on. Similarly, entire V in comes across, again, minus V in comes across the primary winding when S3 and S2 are on. So, only this two factor, what we got in the half bridge, that is missing in the full bridge. So, full bridge as well as half bridge converter, what they do is, first of all, this converts DC to AC. And this is the high frequency transformer. And this, what this does is AC to DC conversion. So full bridge as well as half bridge, both of them, first of all, look at converting from DC to AC. And there is a high frequency transformer for stepping up or stepping down. And finally, there is an AC to DC conversion with a center tapped rectifier. Okay. So in the next class, we will be looking at dual active bridge in detail. Okay.